Hello, in this video we're talking about simple harmonic motion, a very special type of motion indeed that causes waves. Alright, so simple harmonic motion is a specific type of oscillation. And oscillation is a term we use that's a little more general. That means any kind of back and forth motion, specifically around an equilibrium position, some position where it likes to maybe rest. You might hear this in the context of an oscillating fan, like a fan that kind of goes back and forth, like it's saying no all the time. Yeah, so back and forth motion, picture bouncing a rubber ducky on a pond or something, is what can cause a wave, which is why we're interested in this. All right, here are a couple examples of oscillations causing waves. This is a tricky thing because you're going to want to equate them, and an oscillation itself is not a wave. A thing moving up and down isn't a wave, right? A wave is a specific thing. It's a transfer of energy through space through a medium. So here's two examples, like the oscillation, the back and forth movement, in this case, the up and down movement of this rod is making a wave, and the wave travels down this string. Whereas over here, this is a picture of a longitudinal wave. We could picture this as a sound wave. And now you have something like a speaker moving this way back and forth. So this would be an oscillation, the speaker moving back and forth. It is not a wave. The speaker is not a wave. It's a speaker. It's a piece of paper going back and forth. The overall complicated motion of all these particles in such a way that it transfers energy from left to right, that's a wave. A wave is a physical thing. Not something like on a graph. So oscillations are the things that make waves happen. And so we like to talk about the movement of an oscillating object. So simple harmonic motion is a type of motion, a type of oscillation where you get, very kind of clean waves that look like this. Okay, realistically, a sound wave is maybe a little more complicated. The speaker's not moving back and forth such a nice way. This would be like listening to a tone, like the sound at the doctor's office, with a perfect back and forth motion. But that is a specific type of motion called simple harmonic motion. And if we were to graph that motion, the motion graphs would look like sine and cosine waves, which we'll look at. Okay, there are two conditions for simple harmonic motion. This is a very big one from the IB. They really like you to know these. This is a big, big knowledge thing. It does come up a good bit. So you really, really want to memorize these. You will be asked to state these on IB exams. And it's pretty specific, but here's the deal. You will do simple harmonic motion if you're an object whose acceleration is proportional to displacement from equilibrium. In other words, the further away you get from the middle point, the bigger your acceleration is. And also, your acceleration should be directed towards equilibrium. So they're both about acceleration, and the two conditions that you have to memorize are that it's proportional to displacement from equilibrium, and it's directed towards equilibrium. If you prefer, that means it's always opposite of the direction of your displacement, and we'll look at it in that way in a second. Okay, so write those down, put a big star next to them or something. You're definitely going to want to memorize those and cram them before the exams. Okay, here's a couple pictures to think about this. Here's an oscillating mass, a thing going back and forth. No wave is happening here. There's not a wave here at all. There's nothing like carrying energy from one spot to another. This is just a thing moving back and forth. Okay, but so as this thing moves back and forth, the reason it does this kind of motion is because of the spring. The spring is a very common example of a force that's a restoring force, because a restoring force is a force that follows these rules. It's like a force, but a force will cause the acceleration. So the deal with Hooke's law, if you remember this, Hooke's law is an equation where the size of the force depends on your displacement. So if you stretch a spring a certain distance, there's going to be a certain force that the spring pulls with. If you double the distance, you double the spring force. Right? That's our idea of proportional. And the spring force is always opposite the direction of displacement. That's what this negative sign is about. So if you have a displacement to the right, like in this picture, the force is to the left, towards the middle. At rest, it's not doing anything. And if you have a displacement towards the left, the force is towards the middle. So spring is a great classic example of simple harmonic motion because the nature of the force is such that your acceleration will be proportional to how far away you are and will always be towards equilibrium. Here's another little animation to show that idea. So notice the further away you get, the bigger the force is. That's the really important idea. There's a lot of like back and forth motion where you're moving back and forth or moving in some kind of periodic way. But unless this is true too, unless the force trying to make you, chill out, settle down back to your equilibrium position, unless that force gets bigger the further away you get from equilibrium, it's not simple harmonic motion. So it needs to be like this. The further away you get, the bigger the force is. And notice too, it always points towards this center point. So we can kind of just tell it wants to relax, like right here. If we let this thing go for a while, assuming there's friction and so on, it would stop right here. There's an equation version of this definition in the data booklet that looks like this. So this equation is the definition of simple harmonic motion. This, I would say, is the math version of the two sentences we wrote down. So here we have an equation that shows the acceleration of a thing being proportional to x, its displacement from equilibrium, and the negative sign kind of covers this idea of towards equilibrium. So like if x is positive, a is negative, and vice versa. And it looks like the other thing in here, the coefficient of proportionality, if you like, has to do with this thing called angular frequency. So that's the Greek letter omega there. And we're going to talk about angular frequency, which is a way to measure the rate of oscillation in radians per second, which is great fun. And we'll get into that in a second here. All right, but that equation is in your data booklet. That is a great reference for like the rules of simple harmonic motion, as is this here graph. This graph is a super important graph that I can almost guarantee is going to be on the IB exams. They love this graph. It's so weird, acceleration versus displacement. But this is a graph version of this equation. This graph shows acceleration proportional to negative x. Yeah, that's what that would look like on a graph. When x is positive, a is negative. When x is negative, a is positive. And bigger x, bigger a, like in size, magnitude. So this equation is this graph is the graph that defines simple harmonic motion. They're going to ask you about the graph that defines simple harmonic motion. And it's this one. It's not the ones they'll try to trick you with that look all wavy. This is the defining graph of simple harmonic motion. So what's the deal with this angular frequency thing? Well, here we go. We use the Greek letter omega here. That's looks like a W, but officially a Greek letter. And it's very much like angular speed, like we did for HL students in rotational stuff. We measure it also in radians per second. And here it's a way of talking about the rate at which you're cycling and when you're oscillating. So the idea here, which is pretty mathy, is that an oscillation corresponds to 2 pi radians. If it helps at all, we're talking one time around the unit circle or one cycle of a sine or cosine wave. All right, but 2 pi radians is like how much a way you can measure a cycle of something doing oscillation. And so this would define angular frequency. Angular frequency is 2 pi over the period, since period is the time it takes to do a cycle. And if we're saying you do 2 pi radians in a cycle, then this would be that frequency. In the data booklet, this is what you get. So it's this equation just solved for period. So the left side, we've seen before, this is the relationship between period and frequency. And now we're going to throw in this angular frequency guy. And one other fun math thing you can do here that you see a lot is solve for angular frequency in terms of their maybe regular frequency, f. And we're just kind of cross-multiplying the right side here. So this is all baked into the data booklet equation. Just looking at angular frequency itself is something you do pretty often. And this one I think is pretty good to think through what it means. So frequency is, how often you're oscillating in cycles per second. And we're saying there's 2 pi radians in a cycle. So I'm multiplying 2 pi radians per cycle by my cycles per second to get radians per second as like a rate of oscillation. So just think about these things as you practice. They are all about the same idea, and it's just different numbers we can put on it. If this helps, a good way to think of it is period is like seconds per cycle, frequency is like cycles per second, and now this guy, angular frequency, is radians per second. Okay, that's a fun, crazy one of acceleration versus displacement. But how does all this stuff change with time? Well, here's where it gets a little confusing, but also maybe what you sort of expect. It looks like sine and cosine craziness. The graphs look like waves. Okay, be really careful with language and how you say stuff, because a graph is not a wave, just like a graph is not a elephant, right? A graph is just a graph. It's a drawing that shows us how one thing changes with another thing. So if a thing is just bouncing up and down, there's no wave to talk about, right? But if we graph its motion, it will look like a math graph of a wave, right? So just be careful with the difference of an actual physical wave and a graph that looks like a wave, like a sine function. Okay, but so you want to at least be comfortable translating between these with our regular motion graphing rules. So let's say that here's x, like position. If something starts at equilibrium, it goes up and comes down, and then it goes down to some minimum and comes back up to equilibrium. That would be like a cycle, up to a maximum, down to equilibrium, down to some minimum, back to equilibrium, right? So it's moving up and down at these different rates. Remember, the way you can do this is, if you want to talk about velocity, say given a displacement versus time graph, you would talk about the gradient of the graph, the slope of a tangent line on the graph. And so with this example, of course, it can start at different points, but with this example, we're starting the stopwatch when the thing's right in the middle and going upwards, I guess. And it has a positive slope, right? A positive gradient, I should say, the slope of a tangent line. What that means is, for this object, it's got a positive velocity at the time t equals 0. And then that positive velocity decreases, the steepness of this line decreases to 0 steepness here at the top, which means 0 velocity. And then it decreases more to negatives. And then it's really steep negative here for a second. That's a minimum velocity. So this green line has maybe a slope of -2. Yeah. And then that increases, or, goes from -2 to 0, because now it's flat here, so that's 0 velocity. So you get this interesting thing. And if you do the same thing on your velocity to acceleration graph, guess what? You get another like sine, cosine kind of thing. All right, so translating those is exactly the same skills as you use for regular motion graphs. So use the same skills of gradients and so on. If you happen to be a student of calculus and you know what's happening here in terms of a sine function turning into a cosine function and a cosine function turning into a negative sine function, if that makes any sense and anything clicks there, great. You definitely don't need any calculus or anything like that for IB physics, but it can be helpful if you know that a little bit in terms of what these graphs are going to look like. But ultimately, we're graphing tangent lines still is what we're doing. Some other stuff you want to know about simple harmonic motion: energy. Energy is, of course, a thing, and we can talk about the energy of a thing doing simple harmonic motion. The idea is you go between potential and kinetic energy. If we're talking an ideal oscillator, we might say it's, doesn't lose any energy, and so it would go back and forth like forever. Realistically, that's going to lose some energy. That's called damping. But take like a spring. What's happening here is when a spring goes up and down, it's got kinetic energy when it's moving through equilibrium, but then that energy becomes stored in the spring by compressing or stretching the spring. There's some very fun details for a vertical spring where you can, in a math sense, ignore gravitational potential energy, which is a whole fun thing you can derive, and I would encourage you to look into if that sounds fun. But essentially, you're trading off between potential and kinetic energy as you move at different speeds. And a pendulum is another big example of simple harmonic motion, because this pendulum, the bob on the pendulum is what we call it, the mass at the end of a pendulum. As it gets further away from the center here, the components of gravity and tension, kind of pulling it back towards the center, get bigger. And so this is, at least at small angles, a pendulum is a simple harmonic oscillator. And same deal, up at the top of a pendulum swing, it's at rest for a moment, and it's got a bunch of potential energy because it's some height above its like lowest point. And then it gets to its lowest point. This would be equilibrium for a pendulum. And at this point, it's down as low as it can get. So we could say it's got no potential energy, but a lot of kinetic energy. And then it turns into all potential, kinetic, potential, kinetic. So again, motion graphs are the same thing here, same skills here. And so is energy stuff, transformation of energy stuff will come up as well in simple harmonic motion. All that to say, there's not really new skills here to learn, but there's just common things you'll see in terms of motion graphs and energy transformations for simple harmonic motion. So keep that in mind as we practice. And one last thing to practice is let's look at some examples. A very common thing that the IB will ask you to do, and a good exercise to see if the rules for simple harmonic motion make any sense, is to say, here's some stuff happening. Is it simple harmonic motion? Is this simple harmonic motion? Let's see what we think. I'll give you some examples. You should pause the video and make a guess. See if, check your understanding here. Okay, first example. Let's say you're in a car, you hit a speed bump. Now the car is bouncing up and down for a little bit after you hit the speed bump. Is that up and down bouncing an example of simple harmonic motion? Yes or no? What do you think? Make a guess. Yes, that is simple harmonic motion because if you know this, the reason your car bounces is there's shocks, there's like springs that stop you from like stopping immediately, and they absorb some of your vibration. So you're bouncing up and down on springs, and springs follow Hooke's law, so definitely that is simple harmonic motion. The further down the car goes, the stronger the force trying to get it back to its rest position is. So A here is proportional to negative x. Okay, another one. A child swings back and forth on a playground swing. Take a guess. Is that simple harmonic motion? Yes or no? Well, I would say yes as well, because that's an example of a pendulum. As a kid swings back and forth, that's a pendulum. And it's, again, some fun, complicated combination of gravity and tension that are pulling towards equilibrium. And that pull gets bigger the further away you are. There's some fun details that we can get into later about when you're at big angles, things get a little strange for a pendulum, but generally speaking, a pendulum is a good example of simple harmonic motion. Okay, a ball bounces up and down on the ground. Is that simple harmonic motion? Take a guess. What do you think? Yes or no? The answer here is no, that is not simple harmonic motion because your acceleration doesn't depend on how far away you are from the ground. As the ball bounces up in the air and the whole time through the air, the acceleration is always g. The acceleration is negative 9.8 the whole time it's in the air. For it to be simple harmonic motion, the acceleration of the ball would have to get bigger as it gets further away from the ground, and that's not how like bouncing and gravity work. So even though it is a periodic motion, a repeating motion, it's not simple harmonic motion because of that very specific definition. That's like the idea with these. Okay, another one. The moon orbits the Earth with a regular period. What do we think? Is that simple harmonic motion, the orbit of the moon around the Earth? Well, the answer is no. Same reason. That is periodic motion. It's a regular thing that happens, but it would need to be true that then as the moon gets further away from the Earth, it gets pulled more, and as it gets closer to the Earth, it gets pulled less, which is kind of the opposite of how gravity works. And it's moving in a circle. It's not moving like back and forth in a line around a point. This is a type of motion called circular motion, which is its own thing, and is not the same as simple harmonic motion. They do share some ideas like a period and so on. But again, that's not simple harmonic motion. The moon doesn't get pulled different amounts by the Earth throughout its cycle. Number 5, a marble rolls back and forth inside of a curved bowl. Is that simple harmonic motion? Yes or no? Take a guess. The answer to this one is yes. This one's so fun. This is like a pendulum. The math is almost identical to a pendulum. Instead of tension, you have like a normal force. But if you have a ball rolling around in a bowl, it's like the further up on the side of the bowl you get, the kind of bigger of a gravity component is pulling you in towards the center of the bowl. And there's also some fun normal stuff happening here, normal force stuff happening. But it really is the same, almost identical to the same math of a pendulum swinging back and forth as a ball rolling in a bowl. It's also true that this has to be at like small angles and fun stuff like that. But this is typically a good common example that they'll give you for simple harmonic motion. The ball in the bowl. It's a thing. It's so fun. And lastly, a dog jumps up and down on a trampoline. A trampoline. A dog is bouncing on a trampoline. Simple harmonic motion, yes or no? What do you think? The answer is no. Trampoline, you might think, simple harmonic motion, springy something, right? But let's look at this guy. As he's up in the air, same deal as the bouncing ball. The acceleration of the dog doesn't get bigger the higher he goes, right? The acceleration of the dog in the air the whole time is 9.8 meters per second squared. That would have to get bigger with distance for this to be simple harmonic motion. So it is a beautiful phenomenon in nature, just not simple harmonic motion. Okay, so there you go. That's the idea of simple harmonic motion. Knowing that definition and how it applies and applying it to these ideas is really the big thing. So think about that definition as you have some simple harmonic motion fun. See ya.